Stephen Hawking was 29 years old when he discovered that black holes were not black. He was working at the University of Cambridge, already in a wheelchair, already losing the use of his hands, already further into the disease that would eventually take everything from him except his mind. He was 32 years into what his doctors had told him when he was 21 would be a 2-year life. He had beaten that prognosis so thoroughly that it had become almost a biographical footnote, mentioned and set aside, as though the will of the man had simply declined to cooperate with the medicine. He was working on a problem that most physicists considered too difficult to be worth the effort, at the intersection of two theories that were not supposed to be combined, doing the kind of mathematics that most people needed a desk and a notebook and hours of quiet to do, but that Hawking, because he could no longer write, had learned to do entirely in his head. He was lying in bed one night in late 1973, not quite asleep, thinking about black holes and quantum mechanics, and he made a calculation, and the calculation told him something that he initially assumed was a mistake. He spent weeks trying to find the mistake. He went through the argument again and again, looking for the error, because the conclusion was too strange to accept without a fight. He was not the kind of physicist who accepted surprising conclusions quickly. He was careful, rigorous, demanding of his own work in a way that his physical limitations seemed to have sharpened rather than blunted. He went back to the beginning of the calculation and worked forward again. He asked colleagues to check his reasoning. He examined every assumption, and every time he came back to the same answer, there was no mistake. Black holes radiate. They emit thermal radiation, what we now call Hawking radiation, from just outside their event horizons, through a mechanism rooted in the quantum nature of the vacuum. They lose energy as they radiate. As they lose energy, they lose mass. As they lose mass, they radiate faster. And eventually, over an extraordinarily long time, they radiate away entirely and are gone. The discovery was published in 1974 in the journal Nature, and it was immediately recognized as one of the most important theoretical results in physics since Einstein. It did something that nothing before had managed to do. It combined the three pillars of 20th century physics, quantum mechanics, general relativity, and thermodynamics, in a single calculation. It showed that black holes have a temperature, they have an entropy. They are thermodynamic objects, subject to the laws of thermodynamics, which govern the behavior of energy and information in physical systems. The result was beautiful. It was deep. It was the kind of discovery that reveals a truth about the universe that you did not know you needed to know until the moment you learned it, and it was sitting quietly inside its mathematics like a time bomb waiting to go off, a catastrophe. Because Hawking radiation is thermal radiation, and thermal radiation carries no information about what produced it. It is featureless, a random, structureless outpouring of particles whose spectrum is entirely determined by one number, the temperature of the black hole, and nothing else. It does not matter what fell into the black hole. It does not matter whether it was a collection of hydrogen atoms or a Shakespeare play or a human being or a star. The radiation that comes out is the same, a random thermal glow, carrying no trace of what went in. And if the black hole eventually evaporates completely, radiating away all of its mass and energy in this featureless thermal bath, then whatever went in is gone, not transformed into something unrecognizable, gone. The information about what it was, the quantum state that described every particle that made it up, has been erased from the universe. This is the information paradox. And it is not a paradox in the colloquial sense of a puzzling or counterintuitive statement. It is a paradox in the precise logical sense. Two premises that are each well-established and well-tested lead, through valid reasoning, to a conclusion that cannot be true. Premise 1. General relativity describes black holes correctly, and Hawking's calculation of the radiation spectrum, which uses general relativity as its foundation, is correct. Premise 2. Quantum mechanics is correct, and one of its most fundamental principles, unitarity, requires that information is never destroyed, only transformed. Quantum evolution is reversible. If you know the quantum state of a system at any time, you can in principle reconstruct the quantum state at any earlier time, and predict the quantum state at any later time. No information is ever lost. The universe keeps perfect books. These two premises, combined with the result that black holes evaporate completely, produce a conclusion that violates premise 2. Information appears to be destroyed. Quantum mechanics appears to be violated. Something has to give. Either general relativity is wrong in some way that changes the Hawking radiation result, or quantum mechanics is wrong in some way that allows information to be destroyed. Or there is something else entirely, a resolution that neither theory alone can see, that requires a synthesis of the two into a theory of quantum gravity that does not yet exist. These are the options, and physicists have been arguing about which one it is, in papers and at conferences and in books and in late-night conversations and in some cases in public disputes that generated more heat than most physics debates for nearly 50 years. The argument is not resolved, but the search for resolution has produced some of the most beautiful and unexpected mathematics in the history of theoretical physics, and the journey of that search is one of the most extraordinary intellectual stories of our time. To understand why the information paradox is a paradox and not just a puzzle, you have to understand what information means in physics, because it is not the same as what information means in ordinary language. When a physicist says information, they do not mean meaning or significance or knowledge in the human sense. They mean the quantum state, the complete mathematical description of a physical system that specifies to the greatest precision the laws of physics permit, everything about that system. The quantum state of a particle includes its position, its momentum, its spin, and all the other quantum numbers that describe it. The quantum state of a collection of particles includes all of these for every particle, plus all the correlations between them, which particles are entangled with which others, in what ways, to what degree. The quantum state of any physical system is its complete physical description, the full specification of what it is and how it will evolve. Unitarity, the principle that information is conserved, means that the quantum state of any closed physical system evolves in a one-to-one way over time. Every past state maps to exactly one future state, and every future state came from exactly one past state. The evolution is invertible. You can run it forward and you can run it backward. If you know the quantum state of a cup of tea right now, unitarity says you could, in principle, calculate the quantum state of every molecule in the tea 5 minutes ago and 5 minutes from now. If you know the quantum state of a burning piece of paper right now, all the smoke, all the ash, all the light, all the heat, you could, in principle, calculate the quantum state of the paper before it burned. The paper burning looks irreversible to us, but that is a matter of practical impossibility, not physical law. The information in the paper still exists, spread among the combustion products in an extraordinarily complex and practically unrecoverable way, but present in principle in the quantum state of the system. This is what black holes appear to violate. A book falls into a black hole. The black hole radiates for a very long time. The radiation carries the mass energy of the book away from the black hole, but it carries it as featureless thermal noise, with no encoding of the information the book contained. The black hole eventually evaporates completely. The book is gone. The information about the book, not the words, not the meaning, but the quantum state of every particle that made up the book, appears to have been erased, and that is not supposed to be possible. The universe keeps perfect books, except, apparently, in this one case. Hawking's initial response to this situation was to embrace it. He thought information was genuinely destroyed in black hole evaporation, and he thought this meant quantum mechanics needed to be modified, that there was some small but real deviation from unitarity that black holes exploit, in which information is lost to the universe in a way that ordinary quantum mechanics does not permit. He defended this position for years, with characteristic stubbornness and characteristic directness. Hawking was not a man who softened his positions under social pressure. He had opinions, and he stated them, and he held them until the evidence changed his mind. And his opinion on the information paradox was that information was lost, quantum mechanics was incomplete, and physicists who thought otherwise needed to find an actual mechanism by which information was preserved, rather than just asserting that it must be. This put him in conflict with a significant fraction of the theoretical physics community, and in particular with two people who would become his most persistent and eventually most successful intellectual opponents on this question. The first was Leonard Susskind, a theoretical physicist at Stanford who had helped develop string theory and who had a gift for physical intuition as sharp as any in the field. The second was Gerard 't Hooft, a Dutch physicist who had won the Nobel Prize in 1999 for his work on quantum field theories, and who was one of the most respected theoretical physicists of the 20th century. Both of them were convinced that information could not be lost, that Hawking was wrong, and that the resolution of the paradox had to preserve unitarity. They argued with Hawking directly, in seminars and in papers, and they were not successful in convincing him. Susskind has described the experience of arguing with Hawking on this subject as one of the most frustrating of his professional life. Not because the arguments were bad, but because Hawking was extraordinarily resistant to arguments he had considered and rejected, and he was willing to sit in a room full of people who disagreed with him and simply not change his mind. The disagreement became so sharp that Susskind eventually wrote a book about it, published in 2008, called The Black Hole War. The title was deliberately provocative. Susskind knew it would make some physicists wince, but he felt it captured something real about the intensity and duration of the intellectual conflict. It was a war, in the sense that it was a sustained, combative disagreement between people who cared deeply about the answer and were not prepared to yield without a genuine argument. And like many wars, it eventually ended, not with a clean victory for either side, but with a resolution so surprising that neither the victors nor the defeated had fully anticipated what it would look like. The resolution, or at least the beginning of what most physicists now consider the resolution, grew from a direction that nobody had clearly anticipated when the information paradox was first posed. It came from string theory, and from a mathematical relationship called the AD-SS-CFT correspondence, and the story of how it emerged is one of the most remarkable intellectual journeys in the history of theoretical physics. But to tell that story, we have to first go through the history of what physicists tried and why they tried it, because the wrong turns and the dead ends are as important to the story as the eventual progress. They show what the problem actually looked like from the inside, how hard it was to make any progress at all, and how the solution, when it eventually began to emerge, looked nothing like what anyone had been trying to do. The first and simplest proposed resolution to the information paradox was remnants. Perhaps black holes do not evaporate completely. Perhaps as a black hole shrinks to smaller and smaller sizes, something happens at the last moment. When the black hole reaches the Planck scale, where quantum gravitational effects become important, that stops the evaporation. A small, stable remnant is left behind, containing within it the information about everything that ever fell in. The remnant is small but enormously information-rich. It has a mass of roughly the Planck mass, about 20 micrograms, the mass of a large bacterium, but it encodes within it the complete quantum state of potentially enormous amounts of infallen matter. The remnant would be a kind of cosmic filing cabinet, impossibly small, impossibly dense, sitting in the universe indefinitely. The remnant proposal has a certain intuitive appeal, and it was seriously discussed in the early years of the information paradox debate. But it has a deep problem that most physicists have found fatal. If remnants exist and are stable and encode the complete quantum state of everything that ever fell into the black hole, then they are objects with a finite mass and an infinite amount of possible internal states, because there is no upper limit on the amount of matter that could have fallen into a black hole before its final evaporation. A remnant from a large black hole would need to store the quantum state of potentially stellar mass amounts of matter in a Planck mass object. This leads to serious problems in quantum field theory, specifically to a production of remnants in ordinary particle collisions that is wildly inconsistent with observations. The remnant proposal was eventually abandoned by most physicists, though it occasionally resurfaces in modified forms. The second major proposed resolution was the idea that information somehow escapes in the Hawking radiation, that the radiation is not exactly thermal, that there are tiny, subtle correlations in the outgoing radiation that encode the quantum state of the infallen matter, but that these correlations are so small and so deeply hidden that they look exactly like thermal noise, unless you measure the radiation with extraordinary precision over the entire evaporation lifetime of the black hole. This is actually the leading current view. Most physicists now believe that information does escape in the Hawking radiation, and that the radiation is only approximately thermal, and is actually very slightly, very subtly non-thermal in a way that preserves unitarity. The problem is explaining the mechanism by which this happens. How does the information about what fell in get encoded in the outgoing radiation? The Hawking radiation originates outside the event horizon. It comes from the quantum fluctuations of the vacuum just outside the horizon. Nothing that falls into the black hole after crossing the horizon can affect anything outside the horizon. That is literally what the horizon is. So how can the information about infallen matter, trapped behind the horizon, influence the outgoing radiation, which originates outside? This is the deep version of the information paradox. Not just is information lost, but through what mechanism is information preserved, given that the radiation comes from outside the horizon and the information is inside. This version of the question resisted progress for years because nobody had a mechanism, nobody could point to a specific physical process by which information inside the horizon could influence radiation outside. The answer required something that existing theories could not provide, a description of the horizon itself at a quantum gravitational level that classical general relativity cannot give. The person who made the most important step toward providing a framework for thinking about this was Juan Maldacena, an Argentine physicist working at Harvard, who in 1997 published what has become one of the most cited papers in the history of theoretical physics. The paper established what is called the AD-S-CFT correspondence, the anti-de Sitter-conformal field theory correspondence. The name is technical and off-putting, but the content of the result is one of the most extraordinary things in modern theoretical physics, and it is worth spending time on it because it is the foundation on which the current best understanding of the information paradox rests. Maldacena showed that there is an exact mathematical equivalence between two completely different physical theories. On one side, a theory of quantum gravity in a specific type of spacetime called anti-de Sitter space, which is a spacetime with a negative cosmological constant that curves in a specific way. On the other side, a quantum field theory, a theory with no gravity at all, living on the boundary of that spacetime, one dimension lower. A theory of gravity in 3+1 dimensions is exactly equivalent to a theory without gravity in 2+1 dimensions on the boundary. Every physical question you can ask in the bulk gravitational theory has an exact translation into a question in the boundary non-gravitational theory, and vice versa. Every calculation in one language has a corresponding calculation in the other. The two theories are not just similar or analogous, they are exactly dual. They are different mathematical descriptions of the same physical reality. This is the holographic principle made concrete and mathematically precise. The idea that a lower dimensional theory without gravity could encode all the information of a higher dimensional theory with gravity had been proposed by 't Hooft and Susskind in the early 1990s as a general philosophical principle, motivated by the physics of black holes and the Bekenstein-Hawking entropy formula. Maldacena made it specific and rigorous, and he gave the physics community a concrete example in which the duality could be studied in detail and tested. The relevance to the information paradox is profound. The boundary theory in Maldacena's correspondence is a quantum field theory, and quantum field theories are unitary. They obey quantum mechanics. They conserve information. They are precisely the kind of theory in which information cannot be destroyed. If the bulk gravitational theory is exactly equivalent to the boundary field theory, then the bulk gravitational theory must also be unitary, must also conserve information. Any process in the bulk, including black hole formation and evaporation, must have a unitary description in the boundary theory. Information cannot be lost in the bulk if it is preserved in the boundary, and the boundary field theory guarantees its preservation. The AD-S-CFT correspondence, if correct, implies that information is not lost in black hole evaporation, that Hawking's original conclusion was in some sense wrong, or at least that the thermal nature of the radiation is an approximation, and the true radiation preserves information in a way that the approximate calculation does not capture. This was a major conceptual advance. It told physicists what the answer was. It told them that information is preserved, that unitarity holds, that quantum mechanics wins. What it did not tell them was how, through what mechanism, by what physical process, in what way does information escape from behind the event horizon into the outgoing radiation. The AD-S-CFT correspondence proved that information must be preserved without explaining how it is preserved. The proof of existence is not the mechanism, and the mechanism, the actual physical description of what happens at or near the horizon that allows information to escape, remained deeply obscure. The next major development in the paradox came from an unexpected direction, and it generated more controversy than anything that had come before. In 2012, a team of 4 physicists, Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully, published a paper whose argument, if correct, implied that one of the most cherished features of black holes in general relativity was simply not there. The paper is known by the initials of its authors, AMPS. And what AMPS argued was that if information is preserved in Hawking radiation, if the radiation is not exactly thermal but carries information, as AD-S-CFT implies, then the event horizon of a black hole is not what general relativity says it is. The argument is subtle but can be stated roughly as follows. Hawking radiation, as ordinarily understood, involves pairs of entangled particles produced by quantum fluctuations just outside the horizon. One particle of each pair falls inward, one escapes outward. The outgoing particle is entangled with its infalling partner. But if information is preserved in the radiation, if the outgoing radiation over the entire history of the evaporation forms a unitary, information-preserving sequence, then the late outgoing radiation must also be entangled with the early outgoing radiation. The early and late outgoing particles must be entangled to carry the information coherently. And here is the problem. A particle cannot be maximally entangled with two other things simultaneously. Quantum entanglement is monogamous. If particle A is maximally entangled with particle B, it cannot also be maximally entangled with particle C. If the outgoing Hawking particle is entangled with the infalling particle, as general relativity requires for a smooth horizon, it cannot also be entangled with the early outgoing radiation, as unitarity requires. One of these entanglements must be broken. And the only way to break the entanglement between the outgoing Hawking particle and its infalling partner, the only way to sever the quantum correlation that general relativity requires at the horizon, is for something dramatic to happen at the horizon itself. Something energetic enough to destroy the entanglement. A wall of energy. A firewall. The Amps firewall argument said that if you take both general relativity and quantum mechanics seriously, and if you require that information is preserved, then the horizon of a black hole, which in general relativity is supposed to be a smooth, featureless region of spacetime that a freely falling observer crosses without noticing anything special, must actually be a wall of energetic radiation that would destroy anything that tries to fall through it. An infalling observer, in this picture, would not cross the horizon peacefully and continue to the singularity. They would be incinerated at the horizon by a firewall of Planck energy radiation. The physics community erupted. The firewall paper was discussed, argued about, dissected, extended, criticized, and defended in dozens of papers in the months after its publication. It was controversial not just because the conclusion was surprising, but because the conclusion was in tension with general relativity in a very fundamental way. The principle of equivalence, the foundational principle of general relativity, Einstein's happiest thought, says that the laws of physics in a freely falling reference frame are the laws of special relativity. There is no local measurement a freely falling observer can make that distinguishes being in a gravitational field from being in empty space. An observer freely falling into a black hole should not be able to detect anything special happening at the horizon. The horizon is not a locally detectable feature, it is a global feature of the spacetime defined by the asymptotic behavior of light rays. A freely falling observer should cross it without incident. The equivalence principle says so. And the firewall says the equivalence principle is wrong, that there is something extremely dramatic and detectable happening right at the horizon. Hawking himself weighed in. In 2014, he published a short paper titled Information Preservation and Weather Forecasting for Black Holes. Hawking could never resist a good title, which made the startling claim that event horizons do not actually exist in the precise way that general relativity describes. His paper proposed an alternative picture, involving what he called apparent horizons that would dissolve the firewall paradox. The paper was widely discussed and widely criticized, with many physicists arguing that Hawking had not actually solved the problem but had shifted it in a way that reintroduced other difficulties. The episode illustrated how much uncertainty remained even in the basic conceptual picture of what black holes are and what happens at their boundaries. The search for a resolution that did not require either a firewall or the abandonment of the equivalence principle became one of the most active research areas in theoretical physics in the years after Amps, and the most promising direction that emerged, the direction that has produced what many physicists now consider the most important progress on the information paradox in decades, came from combining the ideas of ADS-SLI CFT with a new set of tools for calculating the entropy of Hawking radiation. The key concept is the Page curve, named after physicist Don Page, who calculated in 1993 what the entropy of Hawking radiation should look like over the lifetime of an evaporating black hole if information is preserved. Page's argument was based purely on the mathematics of quantum information theory, without any specific model of black hole evaporation. He showed that if the total system, black hole plus radiation, starts in a pure quantum state, zero entropy, and if the evaporation is unitary, information preserving, then the entropy of the radiation must follow a specific pattern. It rises from zero as evaporation begins, reaches a maximum at roughly the halfway point of the evaporation, the page time, and then falls back to zero as the black hole evaporates completely and all the information has been transferred to the radiation. This is the page curve. It is the signature of unitary evaporation, of information preservation. If you could calculate the entropy of the Hawking radiation from first principles within general relativity and quantum mechanics, and if your calculation gives the page curve, then you have shown that information is preserved. If it gives a monotonically increasing entropy that never turns over, as the naive Hawking calculation predicts, then information is lost. For decades, nobody could calculate the page curve from first principles. The tools were not available. And then, in 2019 and 2020, something extraordinary happened. Two groups of physicists, one involving Ahmed Almheri, one of the AMPAS authors, along with Netta Engelhardt, Henry Maxfield, and Jeff Pennington, and another involving separate researchers working with related methods, published papers that derived for the first time from a microscopic gravitational calculation an entropy of Hawking radiation that follows the page curve. The calculation used a new concept called the island formula, a prescription for computing the entropy of the Hawking radiation that involves, in a crucial and unexpected way, regions of spacetime inside the black hole horizon. The island formula says that when you calculate the entropy of the Hawking radiation, you should not just consider the region outside the black hole. At late times, after the page time, you should also include a region inside the black hole, an island, as a contribution to the calculation. This inside region, included in the entropy calculation in a specific way, dictated by the mathematics of quantum gravity, contributes terms that cause the entropy to decrease after the page time, turning the monotonically rising entropy curve into the page curve. The entropy goes up, peaks, and comes back down. Information is preserved. The island formula is derived from a framework called the gravitational path integral, combined with the ad-est-sleaf-ft correspondence, and a specific prescription for quantum extremal surfaces, developed by Engelhardt and Wall. It is technically involved. The papers are not light reading, but the result is clean and remarkable. For the first time, a calculation within gravitational physics, using the rules of quantum gravity in the context of ad-est-sleaf-ft, reproduced the page curve. Information is preserved. The unitarity of the boundary field theory is reflected, specifically and quantitatively, in the behavior of the bulk Hawking radiation. The island formula papers were immediately recognized as a major advance. Almheri, who had been one of the architects of the firewall paradox, and who had spent years working on the information problem, described the result in terms that conveyed something of what it felt like from the inside. The combination of mathematical surprise and physical satisfaction that comes when a hard problem yields to new tools. The results won several of the involved physicists' major prizes, and the island formula has since been the subject of an enormous literature exploring its implications, its generalization, and its relationship to the firewall paradox and other aspects of black hole physics. But, and this is the honest caveat that the most careful physicists always state, the island formula does not fully resolve the information paradox. It shows that information is preserved in the context of specific models in ad-est-sleaf-ft, and it provides a computational recipe for getting the right entropy curve. What it does not yet provide is a clear physical picture of how information gets out, what the actual mechanism is, what happens at the horizon in physical terms that would allow an observer to understand intuitively how the information encoded in infalling matter ends up encoded in the outgoing radiation. The island formula is a calculation tool. It does not yet have a simple physical interpretation that everyone agrees on. The question of what is actually happening, in terms of the physics of spacetime and quantum fields, to allow information to escape, is still not fully answered. There is also the firewall. The island formula papers do not explicitly resolve the firewall paradox. They show that entropy is consistent with unitarity, but whether the horizon is smooth or fiery remains a separate question that the island formula does not directly address. Some physicists argue that the island formula implicitly requires a smooth horizon, and that the firewall was a phantom produced by an incomplete analysis. Others argue that the firewall is still a logical consequence of the situation, and that the island formula does not eliminate it. The debate continues. The relationship between the information paradox and the nature of spacetime itself has become one of the deepest and most productive research directions in theoretical physics. The slogan, ER=EPR, captures one of the most striking ideas to emerge from this research. ER is Einstein-Rosen. shorthand for the paper Einstein and Rosen wrote in 1935, proposing what are now called wormholes, tunnels through spacetime, connecting two distant regions or two separate universes. EPR is Einstein-Podolsky-Rosen, shorthand for the famous 1935 paper, arguing that quantum entanglement appeared to imply a mysterious connection between distant particles, the paper that Einstein called spooky action at a distance. Both papers were written by Einstein and collaborators in 1935, and they were never thought to be related. One was about classical geometry, one was about quantum correlations. They lived in completely different parts of physics. The ER-EPR conjecture, proposed by Juan Maldacena and Leonard Susskind in 2013, says they are actually the same thing, that quantum entanglement between two particles is, in some deep sense, a wormhole connecting them. That the entanglement of the Hawking radiation with the interior of the black hole is encoded in a geometric connection, a microscopic wormhole, threading through the spacetime. That the quantum information connections that unitarity requires are literally spacetime connections, geometric bridges between entangled regions. If this is correct, and it remains a conjecture, not a proven result, though it has generated enormous and productive research activity, then spacetime itself is emergent from quantum entanglement. The geometry of the universe is not fundamental, but is built up from the patterns of quantum information connections among its constituent degrees of freedom. This idea, that space is emergent from entanglement, that the fabric of reality is woven from quantum information, is perhaps the most profound and far-reaching implication of the black hole information paradox. It transforms what began as a puzzle about whether black holes destroy information into a question about the fundamental nature of space and time. It suggests that the correct way to think about space-time is not as a smooth geometric manifold in which matter and energy exist and quantum mechanics operates, but as a phenomenon that emerges from a more fundamental quantum information description. The information paradox, taken seriously, as Hawking took it seriously and as the people who argued with him took it seriously, leads to a picture in which the geometry of the universe is secondary, a high-level description that emerges from something deeper, and in which quantum information is the more fundamental reality. There is something extraordinary about the arc of this story, and it is worth pausing to feel its shape before continuing. Hawking, in 1974, discovered that black holes radiate. He found a crack, a place where the two great theories of the 20th century did not fit together cleanly. And rather than papering over the crack, he stared at it. He said, "There is something wrong here. One of our theories must be incomplete." He was willing to say out loud that quantum mechanics might need to be modified, a position that most physicists found implausible but that he held with his characteristic combination of intellectual rigor and stubbornness. He was eventually, slowly, and not entirely gracefully, on the wrong side of the debate, not in the sense that he was wrong to take the paradox seriously, but in the sense that the resolution appears to be that quantum mechanics wins and general relativity needs modification, not the other way around. And the journey from his 1974 discovery to the Island Formula papers of 2019 and 2020, from the identification of the paradox to the first real progress on its resolution, took 45 years and involved some of the greatest minds in theoretical physics, produced some of the deepest mathematics in the history of the subject, and generated a picture of the relationship between information, geometry, and quantum mechanics that nobody had anticipated when the journey began. Hawking himself, in his later years, changed his position on the information paradox. In 2004, at a conference in Dublin, he made a public announcement, dramatic in the way that Hawking, who knew how to work an audience, could be dramatic, that he now believed information was preserved in black hole evaporation, and that he was conceding the long-running debate to Susskind and to Hoof. He had been persuaded, he said, by the ADS-SLI-CFT correspondence, by Maldacena's duality, which implied unitarity in the bulk. He paid off a bet he had made with John Preskill, a physicist at Caltech, who had bet him that information was preserved. The terms of the bet were an encyclopedia, a reference book in which all information was freely available. Hawking presented Preskill with a baseball encyclopedia, the kind of book where all the information is in principle recoverable, though in practice buried in statistics. It was a characteristic Hawking move, conceding the bet with a gift that made an additional subtle argument. But Hawking's concession was not complete, and the way it was not complete is itself illuminating. He accepted that information was preserved, in some abstract mathematical sense, in the context of ADS-SLI-CFT. But he remained skeptical that information was practically recoverable, that an observer could actually extract the information about what fell into the black hole from the outgoing Hawking radiation. And this practical versus in-principle distinction is one that physicists still argue about. Quantum mechanics says information is preserved. The Page curve, as reproduced by the Island formula, shows that the entropy of the radiation follows the unitary path. But actually decoding the information from the Hawking radiation, actually reading off the quantum state of the infallen book from the sea of radiation particles it has been scrambled into, would require a calculation of such extraordinary complexity that it is, for all practical purposes, impossible. The information is there, in principle. Reading it is another matter. This is connected to a concept called quantum complexity, the difficulty of performing a quantum computation. Decoding the Hawking radiation to extract the infallen information requires a quantum computation whose complexity is, by some estimates, exponentially large in the entropy of the black hole, which is itself astronomically large for macroscopic black holes. This is not a small computational challenge. It is a challenge so vast that no physical process in the observable universe could carry it out in the remaining lifetime of the universe. The information is preserved but practically irrecoverable in any meaningful sense. Some physicists find this deeply satisfying. It explains why black holes look irreversible even though they are not. Others find it deeply unsatisfying. It feels like moving the goalposts, like declaring victory on a technicality. Susskind himself has spent years thinking about the relationship between quantum complexity and space-time geometry, following the thread from irreconcilable into a proposal he calls complexity or action, in which the geometric volume of the space-time region behind the black hole horizon is directly proportional to the quantum computational complexity of the Hawking radiation. The interior of the black hole is, in this picture, the complexity of the radiation made geometric. The volume of the black hole grows, even after the entropy has started to decrease on the Page curve, and this growing volume is the geometric signature of the growing computational complexity required to access the information that is increasingly scrambled into the radiation. The black hole interior is not, in this picture, a region of spacetime in the ordinary sense, but a representation of the computational difficulty of decoding quantum information. These ideas, irreconcilable, complexity or action, the Island formula, the Page curve, are not yet fully developed theories. They are a collection of proposals, calculations, conjectures, and frameworks that are internally consistent, mutually reinforcing, and pointing in what most physicists believe is the right direction, but that have not yet been assembled into a complete, fully understood theory of quantum gravity. The information paradox is not yet resolved. The firewall is not yet dispelled. The mechanism by which information escapes is not yet physically clear. What has happened in the past decade is that the problem has become much better defined, the tools for attacking it have become much more powerful, and the outlines of what the answer might look like have become somewhat clearer. This is enormous progress. It is not completion. The people who work on this every day, the graduate students and postdocs and faculty members who sit in offices at Harvard and Stanford and Princeton and CERN and Santa Barbara and 100 other places, thinking about quantum extremal surfaces and gravitational path integrals and the entanglement structure of Hawking radiation, are not working on an abstract mathematical puzzle, though the mathematics is extraordinarily beautiful. They are working on a question about the nature of reality, about whether space and time are fundamental or emergent, about whether the geometry of the universe is made of something deeper, the way water is made of molecules and temperature is made of the kinetic energy of those molecules, about whether quantum information is the most fundamental thing in physics, the bedrock on which everything else is built. These are not small questions. They are the largest questions physics can ask. And the black hole information paradox is the door through which those questions are being approached, because the paradox reveals, with extraordinary sharpness, exactly where our current understanding breaks down and what kind of new understanding will be needed to repair it. There is a person in this story who has not yet been given enough attention, and he deserves it. John Wheeler was a physicist at Princeton and then at the University of Texas who was in many ways the intellectual grandfather of the entire black hole information problem. It was Wheeler who coined the phrase black hole. The term had been suggested to him by an audience member at a conference in 1967, and he adopted it with such enthusiasm that it replaced the ungainly phrase gravitationally completely collapsed star within months. It was Wheeler who trained many of the people who did the foundational work on black hole physics. His students included Richard Feynman, Kip Thorne, Charles Misner, and Hugh Everett, among others. a collection of students that any physicist in history would envy. And it was Wheeler who in his later years developed an obsession with what he called the it from bit, the idea that the physical universe at its most fundamental level is made of information. Not matter, not energy, not fields, not geometry. Information, bits. Yes or no answers to questions. Wheeler arrived at this view through decades of thinking about quantum mechanics and black holes and the nature of observation, and he stated it with the confidence of a man who had been thinking about the deepest questions in physics for 70 years and had earned the right to speculate grandly. Wheeler died in 2008, at the age of 96, having lived long enough to see AD-CFT and the first results that suggested his it from bit intuition might be exactly right. He did not live to see the Island formula papers or the irreconcilable conjecture in its developed form, but the direction that the field has taken in the years since, the progressive revelation that quantum information is not just a useful description of what happens in black holes but may be the fundamental substance from which space-time is constructed, is precisely the direction that Wheeler's intuition pointed. He was thinking about it before most of the people currently working on it were born. The good ideas in physics often have a very long half-life. Hawking died in 2018 on Pi Day, March 14th, which is also Einstein's birthday. He was 76 years old, having outlived his 2-year prognosis by 55 years, having done the physics he did in the conditions he did it in, having been one of the most recognizable scientists of the 20th century, and one of the most productive theoretical physicists of his generation, and having left behind as his most important scientific legacy, not the best-selling book or the voice synthesizer or the cultural icon status, but the paradox, the crack in the wall of physics that he found on a night in late 1973 and spent the next 40 years watching people try to fix. He was not there to see the Island formula. He was not there to see the page curve reproduced from a gravitational calculation. He had conceded the argument about whether information was preserved, but had he lived to see the Island formula papers, one imagines he would have had a great deal to say about them. Pointed, precise, probably contrarian in some way that would have generated another decade of productive argument. The paradox is his legacy in the deepest sense. Not in the sense of a problem he created and that reflects badly on him, but in the sense of a question he had the courage and the intelligence to formulate precisely, to state clearly, and to defend stubbornly. A question that has driven some of the best theoretical physics of the past 50 years, and that is still driving it today. The crack he found in 1973 has not been sealed. It has been widened, illuminated, explored, and found to lead somewhere extraordinary, somewhere that looks like the interior of the universe's machinery, the place where information and geometry and quantum mechanics meet in a way that existing theories cannot fully describe. The black hole information paradox is the door into the deepest room in physics, and Hawking found it, and he showed it to the world. The room is still being explored. The physicists who work in it are working with tools that did not exist when Hawking found the door. Mathematical machinery developed in the last 30 years that connects quantum information theory to quantum gravity in ways that would have seemed impossible in 1974. They are getting somewhere. The Island formula is a genuine advance, not a trick. The irreconcilable conjecture, if it holds, is one of the deepest structural insights in the history of physics. The possibility that spacetime is emergent from quantum entanglement is not a speculation but a research program, one with specific calculations and specific predictions and an active community of people testing it in specific contexts. Where it will end, what the final theory of quantum gravity will look like, and what it will say about the fate of information in black holes, is not known. The honest answer is that it is not even known whether the current promising directions are on the right track in a fundamental sense, or whether they are good approximations that will themselves need to be replaced when the deeper theory is found. Physics has been surprised before. The history of physics is a history of theories that worked brilliantly within their domain and were eventually found to be approximations to something deeper and stranger. Classical mechanics was replaced by quantum mechanics, which was stranger. Special relativity was strange. General relativity was stranger still. Whatever replaces the current framework will be stranger than all of them, because it must account for all the strangeness already discovered, and then explain why the equations of quantum gravity, when you look at the entropy of Hawking radiation, seem to know about regions of spacetime inside the event horizon in a way that nobody fully understands yet. The universe is stranger than we know. Black holes are the place where that strangeness is most concentrated, most acute, most impossible to ignore. A region of space so curved that nothing can escape. A boundary beyond which causality, in the ordinary sense, seems to break down. A thermal glow of radiation that carries the secret of whether information is permanent or mortal. A question so deep that the greatest theoretical physicist of the second half of the 20th century spent decades on the wrong side of it. Not because he was not good enough, but because the question is hard enough to resist even the best minds for a long time. It is resisting us still, but less than it was. Each year the tools improve, the calculations deepen, the picture clarifies a little. The room beyond the door that Hawking found has more light in it now than it did in 1974. We are still far from seeing the whole room. But we are inside it now, and the walls are becoming visible, and what they are covered with is the most beautiful and the most important mathematics that theoretical physics has ever produced. Somewhere in that mathematics is the answer to whether the universe keeps perfect books, whether information is eternal, whether the quantum state of everything that has ever existed is preserved somewhere, somehow, in some form that the laws of physics insist upon, even when everything else about a system has changed beyond recognition. Whether the book that falls into the black hole is truly gone, or whether it is still there, written in a language so scrambled and distributed that no conceivable technology could read it, but present, encoded in the radiation, preserved in the correlations, waiting in the mathematics for someone to find the translation. Hawking thought the book was gone. He changed his mind. The island formula says the book is not gone. The mechanism by which it is not gone is still, 50 years after the paradox was posed, the most important unsolved problem in fundamental physics. We are working on it.